Hello, welcome back. So we're continuing our discussion of mods. So last time we talked about mods. I put the definition down here, if you can see that. Definition 2.14 says that A is congruent to R, mod M, if M, the modulus, divides A minus R. And remember, one way to think about this is that A and R are considered congruent if you can move from A to R using a sequence of jumps of size m. So if you can start with A and add m some number of times and arrive at R, or subtract m a certain number of times and arrive at R, then those are considered congruent. That's one way to think about it. That's kind of related to what we called the boxes metaphor from last time. Another way to think about it is A and R are considered congruent if when you divide A by M, so A divided by M, and R divided by M, you get the same remainder. Okay. So if you get the same remainder in both cases, they're considered congruent. And you know, the use of R is from remainder. So I mean, the first case to consider is, you know, if A is congruent to its remainder. So that's the very first case to consider. If A divided by M gives you a remainder of R, then that's the R that you want to first imagine there. But then it goes, it is more general than that though. Things are not only congruent to their remainder, they're also congruent to anything which has the same remainder when divided by M. Make sense? So it's a tricky concept. You should recognize that it's tricky. You should understand that this is one of the harder conceptual ideas in this entire course. Okay, so it's okay to spend time on it, and you should spend time on it. I made an argument in the last video that this is a really important idea through all of math. Literally using mods on the integers is important, but even beyond that, that idea is generalized to beyond the integers in ways that are also very, very important in math. So you're going to see ideas very similar to this in many of your future courses. So in the last video, I made that argument. So it's worth spending time on. Now, I want to now discuss, is this the right page? Yes, this is. Okay. Proposition 2.15 from the book. So in this proposition, we are assuming A, B, C, D, and M are all integers. Okay, so those are integers. And we're assuming that A is congruent to B, mod M, and C is congruent to D, mod M. Okay, so if you took A, you can add M or subtract M a number of times and you would arrive at B. Likewise, going from B to A. Likewise, starting at C, you could add M a bunch of times to arrive at D, or perhaps subtract M a bunch of times and arrive at D. Conversely, you could do the remainder thing. Anyways, okay, so the thing to realize now is that, you know, this symbol, the congruent symbol, it looks a lot like an equal sign, right? Well, that was a very good choice to use that symbol. Okay, so a fella named Gauss, Carl Friedrich Gauss, very good mathematician, was the first one to develop mods. And in his work, he adopted this symbol for mods, and it was a brilliant choice. Don't underestimate the power of symbols. Well-chosen symbols are wonderful. Poorly chosen symbols are terrible. Not only does it look good, but I mean, well-chosen symbols make your life as a mathematician much better. Poorly chosen symbols make your life much, much harder. Because the right symbols allow you to free up space in your mind because they allow you to collapse ideas down in your mind. If every time we worked with mods, we had to use this M divides A minus R definition, and it was just a string of words, and we didn't have symbols like this, it would be far more difficult to actually sit down and work with mods. You would have to work far harder to understand what was going on. With symbols like this, your life's far easier. So it's a good symbol. One reason it's a good symbol is because it looks like an equal sign. And why is that important? It's important because in many ways, it behaves like an equal sign. You know, if you had an equal sign and you had A equals B and you wanted to add C to both sides, you would just do it, right? A plus C equals B plus C. Okay, that's fine. Moreover, if you knew that C was equal to D as well, then you could add C to one side and D to the other, right? Because if these two things are equal, you could add C to both sides. In this case, we'll write it as C. In this case, we're going to write it as the thing that C is equal to, which is D. So this type of manipulation, where you have an algebraic equation and you manipulate both sides simultaneously, that's something that you've been doing for years, right? That was like when you took algebra in middle school, high school, whenever you took it, or pre-calculus or whatever. You did that stuff all the time, right? You manipulated one side of the equation and you did the other side at the same time to solve for x or, whatever. So the good news is that the same sorts of things happen with mods. If you have A congruent to B mod M and C congruent to D mod M, you can do this exact same sort of thing. You could add C to one side and D to the other. Basically, you can add equations. Just like A equals B plus C equals D. Usually it's not written like this, but you could imagine adding the left sides, adding the right sides. And that same sort of thing can be done here. You add the left sides, you add the right sides, and it's still true. Which is not as obvious. If I said, assume that M divides A minus B and M divides C minus D. Is it true that M divides A plus C minus quantity B plus D? I don't know, right? The divides thing makes it confusing. Who knows, right? But this makes it at least visually clear, right, what's happening. We still have to prove that it's true, but the good thing is it is. Okay. Likewise, you could subtract from both sides, and you can multiply to both sides. Now, there's one thing that's missing. Okay, if you add, subtract, and multiply, what's the fourth operation? Division's the sort of the next operation, algebraic operation in line. I'm not claiming division right now. You can sort of imagine, first of all, you can think about that on your own and see if you can think of reasons why I'm not. But we will get to that soon enough, probably in the next video. Okay, so this is true. So let's prove it. And this is good. Proving things helps you first develop theory. Now, this is a good fact. Now we can use this in our later work. And second, proofs are good because they really force you to understand concepts better because you have to work with them. So we're going to try to prove this by working with the concepts of mods. Okay, so in the book, what I do is I have some, in my scratch work in the book, I have, I go back to that, do you remember that direct proofs outline of the way in which most direct proofs work? Well, let me show it to you. So I'll step to the side to make room. So right here, I'll put the first box, which is a box containing just the general outline for how to prove something. So how do we prove something? Well, you can see it right there. Next, what I have, let me pull this up. So you can see the general form is P implies Q. We assume P, therefore we want to get to Q. Okay, so now let's actually get it, let's actually put in these problems' assumptions and what we want to do for the conclusion. So if we want to prove part I, we want to prove that A plus C is going to B plus D, then here you go. So we're going to assume that A is congruent to B mod M and C is congruent to D mod M. So that's going to be the start of our proof. And you can see at the bottom there, what we want to do is we want to conclude, therefore A plus C is congruent to B plus D. Okay, so we're starting to fill in our direct proof outline. And you can see one step, the second line and the second to last line say an explanation of what those mean. Okay, or hey, look, that's what A plus C equal to B plus D mod M means. So those two lines inside those little less than or equal to symbols, it almost looks like. What can we put there? So if we're trying to explain what it means for A congruent to B mod M and C congruent to D mod M, what is going to be the second line of our proof, do you think? Well, look at that arrow. Apply definitions or other results. Is that a hint? The definition of mods. Yes, exactly. So we, definition 2.14. A congruent to R mod M has a definition. It means M divides A minus R. So that's going to be in the second line. Likewise, in the second to last line, before we can move to A plus C congruent to B plus D, we'll have to apply the definition again. So let's now put those up. Let's replace the second line, the second to last line with the definition of those. Okay. Now, what do you think is going to be the next step? Somehow we have to go between saying something about M dividing A minus B, M dividing C minus D, down to another statement about M dividing another thing. Well, assume that was the problem. Forget the mod stuff. Assume I was just gave you a problem 2 videos ago, and I said, assume that M divides A minus B, M divides C minus D, show that M divides A plus C minus B plus D. How would you do it? If this was the divides section, you would say, oh, I know what to do. You apply the definition of divides. So that's what we're going to do here too. So the third line of the proof is going to be saying, well, what does it mean for M to divide A minus B? What does it mean for M to divide C minus D? So that gives you this. You see? And now this is good. So we started with the mods. We turn it into a statement about divides, applying the definition of mod. And then we apply the definition of divide to turn it into just statements about integers. And then through some algebra, logic, techniques, we need to get down to this other statement about integers, at which point we can just apply the definition of divides and then apply the definition of mod to reach our conclusion. Does that make sense? So, that was the scratch work in this, essentially in this book. I provided some more words between these boxes, but that's the basic idea. So, with that, let's actually work out a proof. So, proof, this is the proof of part I. So just like in those squares, we're going to start by assume that A is congruent to B mod M, and let's assume that C is congruent to D mod M. Okay. So what do we do in that proof sketch? We said, well, we know what it means to be congruent. We have a definition for what it means. And in terms of mods, by the way, that's all we have. So it's not like we're going to say, oh, and think about the last 3 theorems we've proven about it. Maybe one of those is useful. No, all we have is a definition. So it makes sense. By this point, we're just apply the definition. So you can either say by the definition of mods, if you don't want to recall the theorem or the definition number. As for me, it's simpler to just write 2.14 since I have it here. 2.14 is the number. By definition, 2.14, what is the first congruence equation means that M divides A minus B. The second congruence equation is equivalent to saying that M divides C minus D. Okay. So we applied a definition. Next up, apply another definition. We once again have a statement using symbols. In the previous case, it was this and the mod, and now it's a divide symbol. Once again, let's look what the definition says about this. So, by the definition of divisibility, which you could just write like that, or you could use the number 2.8. By definition 2.8. M dividing A minus B has a meaning. It means that A minus B is equal to M times some integer k. And M dividing C minus D means that C minus D is equal to m times some integer L. And this is true for some integers k and L. Okay, so there you go. Those two steps make sense? We're just simply applying two definitions. And now, if you, let me step aside. If you quickly, I'm going to pull it up again. If you quickly look back at the last proof outline that I had on the screen, you'll see that we need to apply algebra and techniques to get down to the point where a plus c minus b plus d is equal to m times some other integer, which I call t. Okay? So let me, just for reference, we're trying to get down to the point, I'll just do it down here. A plus c minus b plus d is equal to m times t. That's where we're trying to get to. So do you see how to take this and get there? Yeah, it's what we just discussed, basically. Let's add the left sides of the equals of the equations and the right sides of the equals to each other. So adding equations, we have that a minus b, and really this would be a good place to pause. See if you can pause the video now and on your own finish the proof. The second third of the proof will be just like the first third. Only question is, can you figure out the algebra in the middle for the middle third? And also look back to figure out the last third. But try that on your own, and then then you can unpause and watch me. Okay, so plus c minus d is equal to mk plus ml. Okay. And again, we're trying to get down to this point. We don't have a plus c minus b plus d. We don't have m times t. But do you see how to get there? T just has to be any integer. So on the right-hand side, you could factor out the m, and that gives you a k plus l, which are integers. Way back to fact 2.1, that's going to be an integer. Do you see how to get to a plus c? Yeah, if we just sort of, there's an a, there's a positive c, this is a negative b and a negative d, which if you pull those negatives out, gives you minus b plus d. Okay, so regrouping a plus c minus b plus d equals m times k plus l. I'll delete that. And then you can say, you need to note that k plus l is an integer. It's important to note that because in order to apply the definition to go from here to the divide statement, it needs to be an integer. Otherwise, that definition doesn't apply. So you need to say that it is and say why it is. Okay, so since k plus l is an integer, by the definition, I was going to say by the definition of divisibility, actually just to be consistent, I'll just write the definition number. So by, which is 2.8. By definition 2.8, that means that m divides this thing. M divides this thing, a plus c minus b plus d. Okay. So that has to be an integer. We didn't have to give it a name like t. We can just go directly there. We've just noted that m times an integer equals this thing. That's by definition saying that m divides that thing. Okay. So that's true, which by definition of mods, which was 2.14, which by 2.14 means, well, m dividing something minus something means that the first something must be congruent to the second something mod m. And that's what we wanted to show. So completing the proof. So there you have it. End of proof box. Okay, so does that make sense? By the way, this is the end of the proof just for part I. Maybe we'll do a subscript I. Proof of I is now done. We haven't proven 2i, that a minus c is congruent to b minus d, but it's going to be very similar. You're again going to start a congruent to b, c congruent to d. You're again going to apply the definition of mods. You're again going to apply the definition of divides. The algebra will be just slightly different, and then you will again unwind it like before. A times c, b times d is a little more challenging. So I do not do that one in the book. I leave it as an exercise, which is good. You know, this is a good, these 2i and 2i and 3i, those would be good ones to try on your own. Ways to prove that are easily found on I or with, or sorry, on online or with various AIs, I'm sure. So you can always find an answer, but I would say don't do that. This is a good opportunity. If you're trying to understand this stuff, take a moment or take an hour, however long it takes, and try to work those ones out. Okay, good. So that's probably a good amount of time for this video. Here's a little question for you for the end of it. We didn't do divides. I didn't say that a divided by c would be congruent to b divided by d mod m. I didn't do that. So why didn't I do that? Is that always true? Well, first, go and pause the video to think about it. Well, first, remember, everything has to be an integer when you deal with mods. So first of all, dividing by something no longer ensures that what you're left with is an integer. These combinations definitely maintain integer status, but dividing does not, right? That goes all the way back to fact 2.1. You can multiply, subtract, add, I forgot to add, but you can't necessarily divide and maintain it being an integer. So that's one reason why this doesn't work. Is that the only reason? If you could guarantee that you get integers, is it then true? Is it just that we have to stipulate some extra conditions to say it? Another way to write that is if you can guarantee that you can divide it out, let's write it like this. Suppose you have a times k being congruent to b times k mod m. Does this imply, question mark, I don't know if this, I'm asking you if this applies. Does this imply, since the k's are on both sides, you could cancel it, leaving integers. Does this imply that b is congruent, a is congruent to b mod m? Is that true? If it's just ak congruent to bk, meaning that there is a term that you can cancel from both sides, are you guaranteed that a must be congruent to b? So think about that. Should I tell you the answer? I'm going to cover it in the next video, at the start of the next video. So go and pause the video if you don't want to know the answer. Here it is. The answer is no. It is not. This is not guaranteed. You could have this be true and not have that be true. So try to find a counterexample, meaning try to find an example of A, B, and K, and M for which this is true, but this is not true. So you want this to be true, and you want A to not be congruent to B mod M. Can you find that? And if you can find that, good job. And then the next question is, so there's one value of K which is easier to make this work than another value of K. If K equals 0, then this is true, right? Let M be 5 or something. K is 0. A and B are like, I don't know, 2 and 3. So 2 times 0 is congruent to 3 times 0 mod 5. Yes, 0 is congruent to 0 mod 5. That's true. But 2 is not congruent to 3. Okay, so if K is 0, that's one way around this. One way around this. Or, if M is 5, K can just be anything congruent to 0 mod 5. It doesn't actually have to be 0. It can be 5. 2 times 5 is congruent to 3 times 5 mod 5. 10 is congruent to 15 mod 5. But if you divide out those 5s, 2 is not congruent to 3. So K could be 0, 5, 10, 15, 20, negative 5, negative 10, negative 15, negative 20, anything like that, and you have a counterexample. Now here's the question. Is that the only way to make it work? Is that the only way to ensure that you have this and that? So it is possible to find examples of this. Is the only example K being congruent to 0? Mod M. Well, for that answer, you'll have to give me one more view count. Come back next video, and I'll tell you, the answer. See you then.